This is a monostable 555 timer. Basically, it's wired in monostable mode, the standard way of doing it. And the way this works is if you press this button, which I have, which sends the pin 2 or pin 2 low, because right now it's currently high, with this pull-up resistor, this 470K pull-up resistor. If I press it, the light goes on and it stays lit for the amount of time predetermined by this resistor and this capacitor. This is a 10K resistor and a 22 microfarad capacitor. So it gives you more than 1 second time that's on, and it's monostable. The problem with monostable timer using, or the monostable multivibrator circuit here, is that if I wanted to re-trigger it, I can't with this current configuration, because the way it works is you put it on, and it's just a one-shot deal. So if I keep pressing it, eventually it just times out. It's on its own little timer based on this resistor and capacitor combo. And so for a project I'm working on, which will be a surprise to my viewers that care, I'm going to need a retriggerable monostable circuit. So the way the monostable works, and I have an oscilloscope attached to this, is that I have this red wire going to the yellow tracing of my oscilloscope, and that is the monitoring the output of, or pin 6, which is the charge status of the capacitor. And the way, and then I have this black wire right here monitoring the output, and that's coming in on the blue tracer. So let me zoom out and show the oscilloscope what happens when I press the button. So the yellow tracing is the capacitor, and so when I press this button, the capacitor starts to charge, and it charges to a point which is 2/3 of the input voltage, the power voltage, which is 5 volts in this case. So 2/3 of that is 3.33 volts. Once it gets above that, it automatically triggers the discharge pin, which is pin 7, to discharge the capacitor, and the light goes off. So if I do that, that's what happens. That's the capacitor charging slowly on the upper tracing through the 10K resistor, and once it reaches 3.3 volts, boom, and it discharges. And that's how it goes. See, 3.45 here, because the voltage is a little higher than 5 volts, like 5.2 volts or something. And the amount of time that it stays on is determined by a formula called, that's 1.1 times the resistance times the capacitance. So no matter how many times I push this button, that time is fixed, that the timer stays on. And in this case, it's about 1.5 seconds. So no matter what I do, no matter if I press it again now, nope, it went off. So now, in order to make this retriggerable, we just take a diode and we put the diode from pin 6 or 7 to pin 2. And now, when I push this button, and I push it several times, it just keeps staying on. And when I stop pressing it, it releases. And what I do when I press this button is I basically, since I'm grounding pin 2, I am basically discharging the capacitor through the diode every time I trigger this button. And you can see what happens to the capacitor every time I push the button. It never reaches that 2/3 VCC voltage. And so the result is it's constantly being re-triggered, which is great, because now we're going to use this for a purpose of differentiating between several frequencies in order to determine which frequency is which. So let's try that. So at the moment, I have a circuit here using a CD40-106 oscillator, which oscillates at this frequency. You can see that light here. And it's a relatively slow frequency. In fact, the frequency is slower than the time of the, or about the, a little bit slower than the frequency of the 555 timer, the amount of time that it stays on. So now if I take the output of that oscillator and I put it into the trigger of the 555 timer, let me actually get to go in there. And as you can see, it times out. And it times out for a very short period of time just because the periods of the two are very similar. But you see it's generating these little downward pulses every time it times out. And you can see the capacitor is actually making it to that point, that 3.33 volts point. Now, if I was going to take that and I have this going with a slow capacitor now, so let's unplug this for a second. I'm going to get rid of this capacitor here, and I'm going to put in a smaller capacitor. And that capacitor is going to make the frequency faster. And that's the fast frequency. And that frequency is faster than the on time of the 555 timer. So let's see what happens when I plug that frequency into the trigger and see what happens. And basically, the 555 timer is just staying on constantly. You can see it's just on. And you see the result of what's happening to the capacitor. It's charging and then discharging every time it's re-triggered. And because of that, this monostable 555 timer functions as a frequency differentiator, because when the frequency here is fast, it just stays on. But when the frequency is lower, it goes off. Or it actually goes off and has the little downward pulses. So in that way, we can use the fact that it always stays on versus the fact that it goes off periodically in order to differentiate between these two frequencies. So this way I know, based on the output signal of the monostable 555, if it's actually going to be on all the time, then I know that the frequency that I'm dealing with is the fast one. And if it actually goes off periodically, then and gives you pulses, essentially a signal that you can process and use, then it's the low frequency. And so that is how you can make a retriggerable 555 and use it as a frequency differentiator. So thanks for watching. And here's the schematic for a retriggerable monostable 555 timer.